This is Marc-Oliver Pahl from the Technical University of Munich, and he will tell us now something about the virtual state layer, which will ease the orchestration of smart spaces.
Thanks a lot for the introduction. So, indeed, I will present to you today the virtual state layer, and so briefly to say what my talk is about, when we look at smart spaces today, we don't have apps for smart spaces. And I will tell you why we don't have these apps and what we could do in order to have such apps. So I will first start to look quickly at crowdsourcing, then I will look at smart spaces today, and then I will present to you the virtual state layer, which structures and facilitates the orchestration of smart spaces. So, when I talk about a smart space, what I have in mind is indeed just such an environment. So it's a normal environment that we have around us. And when I talk about orchestration of such a smart space, what I mean is that I perceive something I have in here, and then I do a change on the state of this space, for instance, by stopping the ventilation. So when you see such a space here, there are lots of spots where we could do such orchestration. I just put an arrow to some of them. And interestingly, today you can buy devices to do such an orchestration in shops, so you don't have to buy special equipment for research. You can just go somewhere and buy, for instance, controllable power plugs, where you can switch on and off lamps and so on. But still, what you don't find is apps, so that you can say, like, okay, I want to have an orchestration or a control of all these devices together, so that when I wake up, the TV goes on and the shutters go down or something like that. So let's first have a look at a space where we have apps, and this space is known to you. It's the smartphones. And so for these smartphones, we have ecosystems for applications, and this model is really successful. So just show you these graphs. So here you see the amount of devices sold during the period and the apps available at the end of the quarter. So you see that the amount of apps is also continuously rising. And in this figure we can see that we have about 250,000 developers for these platforms here. So when we add other crowdsourced development models, namely the open source models, then we can see that there are lots of people who like to devote their time on developing software and sharing it. So either for free or for money. And so the idea behind the system I will present to you is, wouldn't it be great if we could have such a movement for smart spaces as well? So it would be great, so I would say yes. But the problem is, at the moment we cannot have it. And why can we not have it, or what are the characteristics of such environments here? So when you look at a smartphone, or when you look at a computer where you can develop software for, you have to define APIs to the operating system and to the things you want to use. When you think on a smart space like this one, then you don't have these defined APIs. So when you want to write a software that orchestrates all devices where you put arrows to, you have lots of work to be done. So there are several things that we would need in order to have a platform where apps can be created on top of. So the first thing we would need are homogeneous APIs. Because then we would be able to access all these devices without specific code. Then we could do something very important. We could create portable applications. And by that I mean applications that you can write here for this room, and then you can run them on different rooms. So this is especially important, and also a big difference to the smartphones, for instance, because each smart space you will find in the wild will be different. So there will probably not be two smart spaces that will be the same in terms of the devices available there. The third is we need dynamic extensibility, because people will always bring in new devices or remove some. So we have to have the ability for changes. And finally, to really have such crowdsourced development, it must be simple to develop for such a smart space. So put it a little more formal here. There are 4 questions. So the first is how can a homogeneous API to heterogeneous devices in smart spaces look like? The second, how can the portability of applications be supported? The third, how can dynamic extensibility be realized? And the fourth, how can the development of applications for smart spaces be supported to facilitate it? So, when we think about smart space orchestration today, like home spaces, and can we orchestrate them? We basically have three models and how it happens. So the first one is the most widespread used. It's a centralized orchestration. So that means we have a physical world, on top we have the sensors and actuators, and then we have services that orchestrate these well-defined spaces here by having interfaces. That means real code for interfacing the specific devices they were designed for. Okay, and here with the arrows you see already, it's quite complicated to write such applications because you have to interface all the different protocols and interaction models of the devices. And it's also difficult to port these applications to other sites because they're written specifically for these sensors and actuators. So what you can do to ease this is the second approach I present to you here. So it's introducing gateways. So you can introduce protocol gateways here, and they ease the process of orchestration a lot because they basically allow service authors to write using just one protocol. And then the gateways are taking care of transforming the protocol messages into the protocols actually used by the sensors and actuators. And so, examples, for instance, in this paper, you create them gateways in between two protocols, and then you have the freedom to write in the language you want, in the protocol that you want to write here. But the problem still remains that you have a tight coupling between the sensors and actuators and the services and the application here, because the protocol is translated here, but still the interaction model remains. So if you have to send certain commands to get something, or if you have to take care of timing, then this issue is not solved by introducing such gateways here. Then the third thing that plays a role in this context are so-called ontologies, so a definition of what can be expressed in the world and how the relationship between entities is. So ontologies are a next level of abstraction, and they can be applied to the services and the gateways here. Okay, so in this paper you find an overview on the current state of the art of ontologies. So when we look at these approaches, we have several criteria we want to look at, because then we want to do improvements. And the first thing is the API homogeneity. So when we look at the centralized orchestration, as I told you already, we don't have homogeneous APIs because we have to write code for each of these different devices here. In the case of the gateways, it's better because we can use a homogeneous protocol, but still we have to take care of device-specific issues. This is why I put a circle here. In the case of ontologies, depends of course on how we use them, but we can have a homogeneous API and especially use high-level concepts. So this is why I put a plus here, because we're talking on a very abstract level, and that makes it possible to use a homogeneous interface. Now, what about portability? So in the first case, there's no portability. In the second case, there's more portability because we can just deploy different gateways on different sites that can, in general, interface different sensors. But the problem still remains that we have a tight coupling. So if we have gateways for certain sensors there, and then we have other ones, it's not guaranteed or not even probable that a software I wrote for space A would run on space B, because the concepts are still too much coupled. In case of the ontologies, that's better, because there we have something abstract. So like a temperature format is the following, and some software below has to take care of transforming what I get from the sensor and actuators here into this format. Okay, what about extensibility? So the first one is difficult to extend it because you have to write code that extends it. But the second one is better to extend, but you still have to write, on the one hand, the gateways, and on the second hand, you have to adapt your code again because you're tightly coupled with the sensors. In the third case, the extensibility is given, but you have to write, but you have to extend the ontologies, and usually what is done that ontologies are something quite fixed. So someone agreed upon something, like a standard, how something should be represented, and then it's difficult to extend it, and it's also difficult, even if it's possible to extend it, that the services use it, because they have to know how the ontology was changed. So then, what about the service simplicity? So here the service is difficult. Here I put an O because the control services are easier here because we just have to run one protocol, but the gateways have to be programmed, so they're complicated. And here it's the same thing, so the control services are easier, but the gateways as middle thing here that transforms the information you get from the sensors and actuators to the ontology are complicated to be done. Okay, so which could be a good abstraction? So to answer that question, what we did is we looked at orchestration tasks. Again, in this home environment or smart space environment. So when we think about it, what humans do, they basically do three things, or often you can structure orchestration and such things. Namely, you have a perception, like it's too dark in here. Then you have a cognition, okay, so I want to have more light, for instance. And then you decide to do an action, like switching the light on. Okay, and so even it's a simple scheme, it fits for lots of orchestration tasks, especially if you think back on the image on the first slide I've showed to you. So they could do lots of orchestration things with just this simple orchestration scheme. If we put it more in a computer-readable form, we would have a very simple form of policies, namely event condition action rules that could express this, and they would look like that. So we had an event, a new luminance was measured, a condition is below 1000 lux, for instance, and then an action, something is fired. When we look at that, we see that a key point here is environmental state. So here, we read some state and we check it for some value, and here we change some state. Okay, and so as state is so important, we decided to introduce another layer to the existing layers we had before. Namely, here are the layers we had before, and so now we decided to make state an explicit layer in between the services that do the orchestration and the sensor and actuator hardware here. Okay, we call this layer the virtual state layer, and an important thing about this virtual state layer is that it's really a logical barrier in between here. So you don't have any direct connectivity to below here, so there's no service that is directly calling a method on such a thing and then a method on here, but these do reflection of the things you have down here into this layer, and these just interact with this one. Okay. To realize this, we introduce here a peer-to-peer network of so-called knowledge agents that contain knowledge trees, which are the representation of the state of the environment. It can be changed and obtained by the actuators and the sensors. So the tasks of the different layers are, this layer does the knowledge brokerage and also the knowledge storage, because this is also an important task of these services here, to keep state and then to use the state to do new tasks. As we have this decoupling, as I told you, we need some entities that do the virtualization of these things, but in another way, as we heard in the talk before. So here they really do, I will show it to you an example in a second, a reflection of what they get onto this layer. And then we have advanced reasoning services. I will tell you something about that also in a second. And and then orchestration logic. So this is where the rules are getting applied on this space. So now to the example. So in the example, we have the sun here, and we have a sensor. And the sensor is measuring the luminosity here, so it's quite high. Then it's packing this into a protocol and sending the protocol message to the gateway, which is the endpoint of the communication for the sensor. Then the task of the sensor is trying to undo this operation here by finding out again, okay, this information here meant it's 5,000 loops, and storing it into the virtual state layer here. Then we can have an advanced reasoning service, and this one is subscribing to this value, getting a notification that there's a new value, inferring some knowledge by doing advanced reasoning, and then storing it here again. So it stores now its day, and then you might have an orchestration logic here that is using exactly this value by subscribing to it again. So here we realize then as well a service-oriented architecture. Okay, so how did we do the decoupling here? So to realize the decoupling, we use the concept tuple space for the process communication coordination. And so it was introduced first with this system, and you have other implementations for that as well. So the basic thing of the tuple space we have here is that we have a producer of information, and this producer puts a type tuple, in our case an address, a type ID, and a value into the tuple space, and then a consumer can subscribe to information here based on the address in our case, or it can query information in here based on the type ID in our case here. All right, so what changes did we do, or which extensions did we do to the original tuple space concept? So here are already changes in the specific nature of the tuples I have here, but it's pretty much the basic tuple space schema, but we did additional things. So let's have a look at the layers again. So here are the layers again. This is another entity I will talk to you about in a second. And so first, and probably the most important thing we have is again this full spatial and temporal decoupling of the entities, which the tuple space automatically provides us in our implementation. Then we have data type-based search, which the original tuple space concept also provides. And then we have a unified interface containing of the methods you just need to access those tuples, which is search, get set, and subscribe. So it's a REST-like API to access these tuples if you have the address, and you can subscribe to those, so it's also a publish subscribe system. So now our changes. So one major change is that our tuples are not living on their own, but they're hierarchically structured. So the reason why we did that is, in a space you have complex entities. So an example is in our lab we have a controllable power plug, and it has a temperature sensor and also 4 plugs. And so then you can represent this in here as a logical tree, saying like, okay, you have a node where you get the temperature, and then you have 4 nodes where you can control the different plugs. Then we have a semantical locator ID split. This simply means that we don't search for knowledge based on the address, so not on the specific instance of the knowledge, but we search based on the type. This is very important because with that it's possible to have different sensors that map on the same representation here, and then we can write these portable applications. Then we have multi-inheritance. So this is important because when you have, for instance, in your ontology a lamp, and then you want to create a dimmable lamp, it should still be of the type lamp in order to make services orchestrating lamps possible to access this model here. Then I started to talk about ontologies. So we also have an ontology. Our ontology is not fixed, but it's dynamically changeable and stored in this so-called model store here. And the idea is that we have a dynamically extensible data model. When someone writes a gateway service here that has to autonomously reflect sensor and actuator state here to this one, he should look up here, okay, what models are already there, and when he finds one that is usable, he should use that, or otherwise inherit from from some of them and create a new model using that. He doesn't have to do it, but if he does it, the advantage is that when there are servers out there that are using the models, then they can also use the new device here. And the last thing here is we have address-based subscription. This is also different from the tuple space where you have type-based subscriptions. This is simply because in a smart space, of course, it matters, for instance, which luminance sensor you subscribe to. It doesn't matter just to get the luminosity of just one luminance, just one sensor inside the house, for instance, but it's necessary to know that it's exactly the one in your classroom, for instance. So, we have the homogeneous API here. We have portable apps through the split here. And we have dynamic extensibility through this ontology that can easily be extended also in a crowdsourced way. So now, how is it mapped on the devices, or how is the implementation? So we have computing devices. On top we have the so-called knowledge agents that store the local knowledge and have the interface search, get, set, and subscribe. On top we have the services, gateway service, control services, user interface services, and other services. And they are connected via TCP, OSGI, or XMPP. So when we have sensors now, they are physically connected to a machine and then logically connected to a gateway service that then reflects the information down to this layer here. And then we have other peers who can have the same things, and this virtual state layer is automatically taking care of keeping the directory here synchronous and routing information in between this network here. Okay, and to do so we have so-called alive things and knowledge object register updates that are sent around. So, now looking again at the criteria we had at the beginning. So we have our solution here now, and as I showed to you, we have a homogeneous API of basically the four methods I just showed to you. We have high portability because of this locator ID split, the semantical one. So we can port apps, assume the same models are used for different devices. It's possible to do that. We're dynamically extensible with the model store. And we have simple control services and simple gateway services. The reason why I put a plus in these two is that both are using this green virtual state layer for communication. And so the one side that is interfacing this state layer is defined as a very easy interface. And of course, with the control service, you have to write control logic, which is essentially what you want to do. And with the gateway, you have to interface the device-specific functionality. Good. So initially, we said, okay, this will be like an easy representation for a task. So how does it look like now when we look on what we introduced? So in our scheme, we can now register a notification handler, and as soon the luminance is changing, we can really just run this test and then change the state, and then the autonomous gateway will reflect the change on the real physical actuator by putting the light on. Having this, it's possible to write applications for smart spaces, and with different models below that, there's also good motivation and also good hope that people will do that because it could be monetized here, and also people devoting their hobby time or their spare time could then really share their software, which is just not possible without such an approach. And so, yeah, our hope with such a system is that more people will have smart spaces in the future because they can have the apps. And so it's the hand and egg problem. So I will buy the hardware when I can do something with it. And at the same time, such a system would make it easy to develop for a smart space. And so many people, like with the applications for the smartphones, who didn't start programming before, for instance, could start programming applications for smart spaces. So I told you part of the whole system today, which is a virtual state layer here for the knowledge brokerage. And with more components in the so-called distributed smart space orchestration system. And the whole system is available online, it's written in Java, has simple APIs that just presented to you and can be used by these interfaces here. So you don't have to write Java services, you can also write C services or whatever it is, the long you can talk TCP, XGI, or XMPP. And you find the repository here. You find also the slides here. And yeah, so let's conclude. So we looked at crowdsourcing first, at the applications for mobile phones. Then we looked at smart space orchestration today, and then we looked at the virtual state layer as something that can structure and facilitate the creation of applications for smart spaces. We have now homogeneous API, portable applications are possible, it's dynamically extensible, and the simple development of services becomes possible. And so we could start orchestrating the space by starting the ventilation again. So here's the URL again, and thanks a lot.
Thanks. Thanks, Mark-Oliver. Very nice talk. Are there questions? We are a little bit behind schedule, but there's always time for 1 or 2 questions.
Everything was clear. That's good.
So
Yes, please.
So I walked out to like the end for a couple of minutes, but did you get, maybe you covered it at the end, but what is the overhead in terms of timing of being able to discover and manage all of these semantic specifications of these services?
So it depends on how you use the system. So if you just have one of the agent instances, then that is neglectable, because then you have directly the notifications in here, and then the gateways are automatically reflecting it downwards. So then you don't have like a big delay. So actually, so what we use is we use web services and other technology down here, and so they had so huge delay that we could not find out like how much the delay.
So compared to that, this was
it was not significant. And if you use multiple of them, it depends on the configuration, because we only periodically run those updates. And if you set it to several seconds, then in the worst case you have to wait these seconds plus the transmission time, and then you can reflect it here. So the system is not designed for real-time changes. So this is more for asynchronous changes where it doesn't go for seconds or something like that. Yeah.
Thanks. Another question? Yes?
Actually, I'm wondering about the overhead in terms of the size. Is it possible to port it to embedded devices like commonly used by smart spaces?
So the system, the concept, I would say yes. The implementation we have definitely not at the moment, because it's about 2 megabytes, I guess. So only this one, and it's so at the moment we only have an in-memory version for this storage here, and that means it's easily consuming lots of megabytes of your RAM. But we're currently working on a disk-based solution, and then it will be better. But if we would want to put this on embedded devices, we definitely should go for implementing this in C, for instance, but we didn't do that yet. But from the concept and the interaction we have here, I would say it's possible, but we don't have an implementation for it.
Okay. Yes. I have a final question, because I've seen you told us that you have software as open source in Git. I wondered if you also have a working example already in place of such a smart space fan that you can stop.
So we have one, but we don't have a deployed version running at the moment.
Okay.
So what I have, what you also find on the website, is a video which we made already about 1.5 years ago, I guess, where we used the predecessor of this system to orchestrate such things. And what I could also do is just starting it in Eclipse, where we wouldn't see much. So, but it's also something that is planned to have again, because what we have is also a PHP map-based interface where you can then tap on a screen, for instance, to switch things on and off, and then you also see how it interacts. So in the video you can see it, but I don't have like a remotely controllable instance running at the moment where I could do something.
Thanks.
Okay, thank you very much.